Hello, this is a video for the Evidence2 state feedback in discrete time. My name is Fernando, and I will talk about the different aspects. So first, I have quite a important notes to make that I have already made. What is a discrete time space model? How does it differ from a continuous time state space model? Well, the first one that we can see here, both equations are in continuous time, in which we have matrix A and matrix B, which are matrices with values, which are input values. And the matrix C, it's a matrix where we have the output values. It is quite similar to state space model in discrete time mode, let's say. But the difference is that we add an additional feature that almost all the discretized models have a sampling period, in which, since we are not taking samplings, we are not sampling all the continuous time, we are just sampling it, making dividing it by certain periods. We have a value that will be t, that it is about the sampling period. So very curious feature of this value is that if we change it, our matrices A and B will be far different from the ones in continuous time. So yeah, the difference is that we also have two input matrices and one output matrix from continuous time to discrete time state space model, but the difference is the sampling period. What is meant by state feedback with observer? Okay, so we know that state feedback it is a controller, but we also sometimes, when we can observe the behavior of the plant, we have to put an observer, such a kind of tachometer to measure the speed of a vehicle when we don't know exactly, like in real time, the dynamics of the motor. And yeah, it helps us to estimate the behavior of the plant, and with that help the controller to make the desired output possible, in which, as we can see, we have a -k model that is multiplied by the observer. What is the procedure and which MATLAB functions are used when designing a state feedback controller with observer? Well, in my own procedure, I think the most important ones are to define the system in continuous time in the space state model, for example. It could be also first transfer function. Then, when full state feedback is unavailable, an observer is used to estimate the state x. And how we can check this observability through the matrix of observability. That if it's invariable, it's observable. If not, it's not. Convert then the state space model into observer canonical form, which will help us in this form to continue designing the controller. Then we discretize the OCF with the first picture on the right. And after that, we will obtain two matrices, such a kind of A and B from the state space model, but phi and gamma. Then, with the phi matrix, we'll determine, and if a necessary and sufficient requirement for stability is that all the eigenvalues of this matrix are inside the unit circle in the Z-plane graph. And as you can see, also we have an L vector, which has L1 to Ln that multiplies x1 to xn. And then it's a kind of, it helps us for the linear state feedback. Then here is all the procedure. But the most important things are that we will obtain in the third image, the one that it starts with a determinant, a characteristic polynomial. And also, as you can see, are roots from poles, pole 1, pole 2, that are the ones that we are given or choosing for a desired placement of those poles. And after that, we will obtain, after the characteristic polynomial, we will obtain a set of coefficients of the desired characteristic polynomial with beta 1 and alpha. Then the main functions that we used in the last sessions and here were Ackermann's method with the Acker command, which you use it, but the best one in terms of more stable method or more precise is place. Yeah, that has the same arguments. And as you can see, with that, putting in MATLAB, we can avoid all the calculations previously mentioned. And how should the closed loop poles be chosen when working with discrete time systems? As you can see, here we have two important maps, in which the first one explains us that the stable area from the S-plane map or graph goes from infinity minus infinity to the region, and it is all that area. But in the C-plane, it only goes from the region to a unit circle all around the four sectors in this case, in which the limit to determine if it's stable or not, it's the circle. And then, as you can see in the right picture, the poles placed in the region they will have the fastest response. But if they are away from the unit circle, they will be not only unstable, but their growth will be exponential. And if they are in the unit circle, in the border or perimeter of it, they will have the best fast response without compromising their stability. And as you can see, it's not only the let's say the coordinates, but also the angle made with them from the region to the pole placement or the pole position that will also determine the frequency. For example, if you have a pair of conjugate poles, and if they have a certain angle, we can determine the frequency, if it will be just too oscillatory or not, on all those kind of arguments. Then the final choice of poles, we have here the poles that were input, they were changed to the and given to the controller in order to give to fulfill the requirements. In the first picture or graph, we can see that it is about the scope in Simulink, which is called trolley force, in which indicate us how much newtons were given as input. In this case, it is below the maximum force allowed, that were 40 kilonewtons. In this case, it's below 20 kilonewtons, so it's okay. Then we have in the right one, unit step, a nonlinear output and a linear output, that thanks to the linear output, we have not just a stable one without oscillations after certain period of time, but also with no overshoot. Then we have a final to verify the settling time that fulfill the requirement that we were required to have a settling time less than 30 seconds. We use the command step info, and here are the results. And then for the last requirement about the bandwidth, we did it with a bottom load, reaching -3 decibels around it, and we obtained 0.2 and something else rats. That was almost the requirement given. Then conclusions. I think this activity was well planned, since it's a continuation from the previous one, and I love that because you can see how are the dots and how you can connect them and apply them in a real life situation. In this case, our gantry crane. So yeah, certainly I will use it because I am working with my team quantum robotics in the control, not only the control, but the design of 4-degree freedom, I think, or 3-degree, I'm not sure, of a robotic arm. So yeah, obviously, I think I will choose a discretized system because we will use Arduino, and I'm not sure if Raspberry Pi, but one of those. And obviously, we can't go for a continuous time system. And yeah, that's almost an immediate solution or application that I will give to all the knowledge acquired during these 10 weeks. And yeah, it's quite interesting, this topic. It is not easy to explain, not easy to understand, but after researching on the videos of Ryan Douglas, I think I have understand very well this topic. Thank you.